for joining in. So thanks everyone for joining for the second part, if you're still there. So in the second part, I want just to give a motivation about what is complex multiplication for abelian varieties, and then explain how it's used to prove the theorem that I just wrote about. So a motivation for this is the following theorem. That's actually not so difficult to prove. So let E be an elliptic curve. If G acts by multiplication on E by an automorphism on E, then E is isomorphic to EJ. So the idea is that if you want G, which acts by C to C by multiplication, to act on C quotiented by lambda, then it must go to the quotient, so it must be that G lambda equals lambda. That is to say, lambda is invariant by a rotation of 2 by 3. And there's only one lattice that's invariant by the rotation of 2 by 3. It's the triangular lattice. Which is the lattice generated by J. So C quotiented by lambda is C quotiented by Zj is Ej, as defined before. So you see, for multiplication by J to X, you have no choice for lambda. You only have one solution. And remark, you can do the same for I. It only acts on EI. And same for omega, it only acts on E omega, which is the same as EJ. So as a conclusion, if you want a complex curve, like a curve on which you have a special automorphism, like an automorphism that's not just times minus 1, or that's not just a translation, you want really something special, you have two options. You have EJ, on which you have multiplication by J, and you have EI, on which you have multiplication by I. And that's it for the special automorphisms. So that's all the elliptic curves. On which multiplication by a root of units is an automorphism. And now we want to do the same in higher dimension. And so to do the same in higher dimension, So why do we want to do the same in higher dimension? Let me recall the theorem. So the theorem is that if the quotient admits, you have a group action. So this group action is going to tell you something. You're going to have elements in the group, and these elements in the group are going to have some J in them, maybe, or some U7 in them. And that's why you're going to have some EJ or some EU7 in A. And so it all starts the motivation for the theorem. So lemma to prove theorem is the following. Let A be an abelian variety and the same hypothesis, and it is the theorem J finite group acting freely in codimension 2 on A. If A quotiented by J has a resolution that is Calabi-Yau, then J is generated by matrices of the form, so up to a conjugation, diagonal, a lot of ones, and J, 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 and same, after diagonalizing a lot of ones and the 7th root of units, its square and its 4th power. Two options. So proof of the lemma, I won't do today. Proof of the lemma is local singularity theory, say. So it's a bit of algebraic geometry. It's a bit of Mackay correspondence for those who know what it is. And so let's forget about the proof. This lemma says that in my group, all elements have this form or this form. And so if my group is non-trivial, which we suppose it is, then it has at least one element with some J's or one element with some zeta 7. So what we want to prove at the corollary is A isogenous to something times EJ 3 times, or A isogenous to something times EU7 3 times. So you see what we want to do is to take this, where is my pen? Okay, to take this eigenspace and to integrate it to this guy, or this eigenspace corresponds to this, the tangent space to this. And now this other eigenspace will correspond to this. And this other eigenspace will correspond to this. And here you may be surprised with the U7 that this relates. And the reason why is that U7, actually, I told you it's -1 plus I square root of 7 over 2. Actually, it's also the trace of this matrix. So here you see the relationship between the two. So the point is what? The point is to say that so the point is the following lemma. If diagonal one J acts on A, then A is isogenous to A primes times EG cube. And the proof of that is very easy. Sorry, no, not so easy, but the first part is very simple. The first part is to say that A prime will be what? A prime is just, so if we call this guy small j, A prime will just be the kernel of J minus identity. And A prime prime will be the image of J minus identity. And now you have something that's like the rank theorem for vector spaces, but for abelian varieties, that tells you that A is isogenous to A prime times A prime prime. And now the question is, J restricted to A prime, on A prime, J is the same as identity. Because it's a kernel of J minus identity. And on A second, J will be the same as the rest, which is G identity A prime prime. And A prime prime has dimension 3. Because you have 3 eigenvalues like this. And so now we are left with one question. Which is, if G identity 3 acts on A prime prime, does it mean that A prime prime isomorphic to EG cube? So same thing as we did at the very beginning with J acting in dimension 1, but in dimension 3 with J identity. And the answer is yes. And how do we prove this? Well, the proof is not so difficult. So the proof is the following. So you take lambda such that A prime prime is C3 over lambda, so the associated lattice. And now the point is, again, G identity to the 3 acts on lambda. Right? Because it acts on the abelian variety, so it has to preserve the lattice. And now what does that mean? Lambda is already a Z module because it's an abelian group, it's a lattice, so it's Z to the power 2n. It's isomorphic to this. It's something where if you sum, you stay inside. So it's a Z module. And now, since it's a Z module and it has this linear action, so this is a linear action because you act by a matrix. Lambda is also a Z bracket J module. Because you have Z bracket J acting on lambda by lambda goes to, by A plus JB lambda goes to A lambda plus B G lambda. So you can just act, and this is still in the lattice. So this is still in the lattice. And so you have this action. Which makes lambda into a ZJ module. And now magic is that ZJ is a principal ideal domain. Some people write it PID. And why is this magic? Because every finitely generated, so it has a finite basis, just like lambda. Finitely generated has a finite basis. Torsion free, so if you sum an element many times, you never get 0, and it's the same in lambda. If you are in a lattice and you take one vector and you sum it to itself a lot of times, you never go back to 0, you go very far in one direction. So lambda is torsion free. So every finitely generated torsion free module over a PID is just the PID to some power. That's the structure theorem for finitely generated modules over a principal ideal domain. And that means that lambda is just vg to the power 3. And that means that A, here I'm hiding some details, that A is C3 quotiented by ZJ cube. Which is this, which is ZJ cube, as we wanted. So here I'm hiding a little bit, in fact, to factorize by the power, because we have to check that the embedding of ZJ in C is really coordinate by coordinate the embedding that we want. But this I won't discuss tonight. The upshot of this is really that from the structure of lambda here, you're done, because you know the lattice is a good one. So the Abelian variety is a good one. And so that's the proof of the corollary here in this case. If you have one element in J that in your group that looks like this, then you know in your Abelian variety you will have one factor like this. And now we come to the second lemma. And the second lemma is the second case. If you have an element like this that acts on A, then A has to be isogenous to A prime times EU7 to the power 3. And this is where we need complex multiplication. So proof goes A prime is the kernel of, so if we call this guy H, of H minus identity, A prime prime is the image of H minus identity. And now A prime prime has dimension 3, and H restricted to A prime prime is the matrix zeta 7 squared, zeta 7 to the power 4. And now the question is, is A prime prime isogenous to EU 7 to the 3? Or why? So maybe a first remark is that on U zeta 7, on E zeta 7 is not acting by an automorphism. That is what we discussed before. We said if you want a root of unit to act by an automorphism, it has to be J, I, or omega. And zeta 7 is not J, I, or omega. So it can't act on E zeta 7. So this is the reason why we can't conclude that A is isomorphic, A prime prime is isomorphic to E zeta 7 squared. So now with U7, we need to define complex multiplication. So definition. So we have two definitions. First, we'll define a CM type. So a CM type is first a field, K, totally complex. So that means if you embed it in C, you never get in R. Quadratic extension. Of a totally real number field of degree n over q. So that's the main data, and then secondary data is a lot of embeddings of K in C. That are pairwise non-conjugates. So an example for this. K equals Q brackets G quadratic over Q. So here degree n is 1 with embedding. So how do you embed Qj in C? Well, you just send 1 to 1 and J to J. So that's the obvious example. And so this is really complex multiplication as we thought. And now maybe a less obvious example is you take K equals Q brackets zeta 7 which is quadratic over Q brackets zeta 7 plus zeta 7 to the 6th, which is an extension of a Q. And you can check if you call this guy A7. You can check that A7 cube plus A7 square minus 2A7 minus 1 is 0. So Q zeta 7 plus zeta, so sorry, QA7 has degree 3 over Q. Because of this 3. So that's another CM type. And that's the one we're interested in. And you have 3 embeddings for this one. So if you try to embed Q zeta 7 in C, you have sigma 1, which consists in taking zeta 7 to zeta 7. You have sigma 2, which takes zeta 7 to zeta 7 squared. It's like the Galois conjugates for those who have done Galois theory before. You can take it to any other root. And here I just picked these 3 ones, sigma 1, sigma 2, and sigma 3 to zeta 7 squared, and zeta 7 4. So this is a CM type. And now what about an Abelian variety with CM type? So an Abelian variety A has CM type K and the sigma 1, sigma n, if dimension of A equals n, and K embeds by a representation rho in the endomorphisms of A, so K embeds by representation in Q such that so Q embeds in Mn of C, so you embed Q in the, you take K and you want to realize its elements as endomorphisms of A, so as matrices. And if you do that, you want this realization of K as matrices to be the same as, so to be conjugates to the diagonal sigma 1, sigma n. So you have one way of embedding K in M and C, and you want this to be the way that K embeds in the endomorphism of your torus. And so an example, if A has diagonal of zeta square, zeta 4 acts on it. Then it has CM type. The CM type we just defined before with k zeta 7, sigma 1, sigma 2, sigma 3. And now we're down to one lemma. So to one theorem maybe first, that's from Shimura, that if K is Q, if K is a cyclotomic field with n smaller than 23, so 7 is an example, then there is a unique abelian variety of CM type K. So corollary for us, since we know that A has CM type this, there is only one possibility for our A prime prime with the action by this element. And now, which is this possibility? Well, here we're going to do some Galois theoretic magic. You have K. So K is Q zeta 7. That's an extension of degree 2 over Q zeta 7 plus zeta 7 to the 6. That's of degree 3 over Q. And now you can also say that this is an extension of Q U7 over Q. And here you have degree 2. And here you have degree 3. So if you want, you can rewrite this tower of the extension as another tower of extension. And these are all Galois extensions. And now the magic is, this implies, again, by a theorem in Shimura, that this is also a CM type. And this is a CM type with n equals 1. So it corresponds to an elliptic curve. And there is no choice here, it's to the elliptic curve EU7. And now here you have a 3. And by the theorem of Shimura, this implies that A prime prime is isomorphic to EU7 to the 3. So every time you have a CM type and it's a Galois extension of another CM type, then your abelian variety is a power of with the big CM type is a power of the small CM type. Here you have the larger CM type, and here you have the smaller CM type. And that's it. That ends the proof of that ends the proof of this corollary. And so now we're almost done. We know that our Abelian variety has some EJ in it or some EU7 in it. And now what we do, so back to the proof of the theorem. So complex multiplication told us that A isogenous to EG to some power times EU7 to some power times A prime with alpha or beta positive. So without loss of generality, we can assume alpha is positive. That gives us a fibration of A on AG alpha. And if we're a little bit more careful, we get a fibration of AJ over AJ alpha quotiented by J. So this is, in fact, J equivariant. And now we have a fibration like this. And so here, AJ has, here we have a volume form downstairs. And so it pulls back, and AJ has a holomorphic form of degree alpha. So this implies that pulling back again, X, the Calabi-Yau resolution, has a holomorphic form of degree alpha. So alpha equal n, and this is the volume form on X. Because on Calabi-Yau varieties, you don't have any form except for the volume form, which is an n form. And since alpha equals n, the dimension of A, which is the dimension of X, it means that A is actually isogenous to EJ to the n. And beta equals 0, and A prime is nothing. And that concludes the proof. So maybe I think I can stop here and just say that we used this little trick on fibrations of Calabi-Yaus and mainly complex multiplication and this lemma on which elements you have in the group to prove the theorem. And the main idea to remember from this seminar, I think, is that when you know some elements acting by automorphism of an Abelian variety, then complex multiplication tells you can predict which Abelian variety it is just from the automorphism.